Mmm, I love fries. Chemistry and love have something in common. In both cases, it's what's on the inside that counts. We chemists are driven by the desire to understand the composition of substances, to see what's on the inside. When we say the composition of substances, we're talking about the type, ratio, and arrangement of atoms within the molecules of those substances. We can understand composition in a number of ways. We conduct conversions and calculations with units like particles, mass, and moles. No, not the furry tunneler in the garden. A mole is a unit in chemistry, but we'll get to that in a minute. One substance that's easy to talk about in chemistry because it's in most people's homes is table salt, which is sodium chloride, NaCl, like I have here. For dietary reasons, some people try to limit or avoid salt, but table salt is delicious on fries. In order to satisfy salt cravings, some people use table salt substitutes. One common salt substitute is potassium chloride, KCl, like I have here. But why does potassium chloride work as a table salt substitute? In part, it tastes similar to table salt because both elements appear close to each other on the periodic table. And if we look at the atomic scale, both compounds consist of lattices composed of positive and negative ions. Notice that while similar, potassium atoms are larger than sodium atoms, and we'll see why that's important later on as well. Okay, so potassium chloride might be a reasonable substitute at the atomic level, but if I sprinkle my French fries with potassium salt, will it really taste the same? Normally, when we eat and drink, we aren't seeing or thinking about substances on the atomic level. We aren't measuring the number of atoms. Instead, we perceive and measure food and drinks at the macroscopic level. For instance, in my kitchen, I use a teaspoon, tablespoon, or cup to measure volume. I also use a scale to measure mass in grams. I'm not thinking at the atomic scale when I bake. So, how can we bridge the gap between the macro world of teaspoons and grams to the atomic world of moles and atoms? And why is it important to do so? Let's explore this by actually seasoning some French fries. Yum. For this demonstration, I'll add 1 spoonful of table salt to my fries. Now, let's try adding 1 spoonful of potassium salt to this second batch. Most bakers would say, you can't do that. They are not equivalent. You have to measure the weight, not the volume. That's because good bakers know weight is a more precise measure than volume. So let's use these scales to weigh the potassium salt and see if it's the same mass. Okay, first, sodium chloride. And now, potassium chloride. And look at that. The bakers of the world would be right. This spoon of table salt has a mass of 10.8 grams, while the potassium salt has a mass of only 9.9 grams. Maybe I should add a little more potassium to match the mass of table salt. To achieve a similar mass, I would need to add about 1 more gram of potassium salt. Okay, perfect. Now I'll add it to this third batch of fries. But as a chemist, maybe the macro views of volume and mass are not what's important here. I think we should replace the sodium chloride with the same number of potassium chloride molecules. To achieve this, we can use a practical and standard way of referring to groups of atoms or other atomic scale particles. Due to the small size of atoms, it's most convenient to discuss groups of atoms in large quantities, like really large quantities. When you're ordering donuts, for example, you can order 12, which we call a dozen. You can order 24, a case, or you can order 144, a gross, which is how you might feel if you eat that many donuts in one sitting. These terms make it easier to talk about quantities of items as opposed to using the specific numbers themselves. In chemistry, we have a similar tool for talking about quantities of atoms, and it's called a mole. A mole is shorthand for about 6 times 10 to the 23rd particles. To be clear, that's a 6 with 23 zeros after it. While it sounds delicious, it's probably not a good idea to order a mole of donuts because it would actually cover the entire Earth in a layer 5 miles deep. That's a lot of donuts. Having the concept of a mole is so helpful to us chemists. It makes it so we don't have to deal with cumbersome exponents like 10 to the 23rd. To calculate the moles of sodium chloride in our sample, we just need to divide by its molar mass. So we have 10.8 grams sodium chloride times 1 mole of sodium chloride per 58.44 grams of sodium chloride, giving us 0.185 moles sodium chloride. Similarly, we can calculate the moles of potassium chloride. 9.9 grams potassium chloride times 1 mole potassium chloride per 74.55 grams potassium chloride gives us 0.133 moles potassium chloride. That's a difference of 0.052 moles between our two samples. To achieve an equal number of sodium chloride and potassium chloride moles, we need to figure out how many grams of potassium chloride to add. In order to do this, we take that 0.052 moles difference and multiply it by the molar mass of potassium chloride. So, 0.052 moles potassium chloride times 74.55 grams potassium chloride per 1 mole potassium chloride gives us 3.88 grams potassium chloride. Therefore, we'd want to add 3.88 grams more potassium chloride to our original amount, which, if you remember, was 9.9 grams. Okay, let's measure that out. This brings us to a total of 13.78 grams potassium chloride. Now, our samples have equal numbers of sodium and potassium ions. Let's add this to the 4th batch of fries. Well, I'm getting hungry, so it's time for a little test. We now have 3 different samples of potassium chloride based on 3 different hypotheses about how to substitute potassium chloride for sodium chloride. One based on volume, one based on mass, and one based on moles or number of particles. Let's see which of the potassium chloride fries tastes closest to the sodium chloride fries. Hmm. Mm. 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 The mole-based sample might be closest in terms of atoms, but not really in taste. It's kind of bitter. I'm not sure I like the potassium salt. In my defense, we chemists are known for our chemical insights, not our cooking intuition. Maybe next time I'll just add some pepper instead.